can involve, say some conditional statements, but it does not loop, then it will finish in some finite time, right? There's a limited amount of instruction it can execute. So we can simply enumerate all possible execution paths. It's possible because there is a limited number of them, and then one by one check that in each state some property holds. But we have loops, right? Then when we do not know how many instructions will be executed. So we cannot be sure that we will visit all the possible program states. Okay, so you may ask, what is the way to deal with loops, how to prove properties about them? And the common way to go is to, well, construct a statement named a loop invariant, which is true in each iteration of the loop. And then if you have something like that, you can prove that after a loop exits, some conditions hold. And I intended to show you an example of simple loop proving with a tool named Caduceus. This time it would deal with a simple C program, but as you are a little bit late, perhaps you have time at the end. If there is not much question, I will return to this slide. Okay, another issue is two terms, verification and checking, which should not be confused. Usually by verification, we mean proving all properties of a program as a whole. So it usually requires to have a program specification. You must know what you expect from a program, and then you can prove that this program really does what it was supposed to do. And it's really expensive for many reasons, regardless what tools you use. But there are quite spectacular examples of successful application of such a verification approach, proving the whole of a program. For instance, often quoted example is specification of Java card API in JML, which stands for Java Modeling Language. And then it was possible to prove Java card applets, to prove properties of Java card's applets, which was pretty large achievement. But there is another idea which is pretty much explored recently. Okay, we know that proving program properties is very difficult, expensive, and close to impossible. So maybe the idea is to shift the burden to the code author, right? Say we have some Java virtual machine and we accept some applets from potentially untrusted source, and we may demand that the only condition that we run this applet is if they come with the proof of the property, of the correctness, right? If only you have a proof from an author that the code does not do, say, any harm to our machine, then we may allow to run it. And this idea with proof-carrying code is, well, a part of a larger framework, which is pretty much explored at the moment, but well, I may assume if anything will result from this research, it will be many years ahead, so we should not devote too much energy to that at the moment. Okay, and another approach is checking. Well, checking is quite a common word, but in this context it stands in a very precise meaning. Checking means proving particular, usually local properties of a program. So we're not very interested in the whole behavior of a program as a whole, but we just want to figure out some very local properties of a program. And it's very similar to a typical security audit. For instance, if you audit a C code, right, usually the first thing you do is to check whether it uses some unsafe library functions, like strcpy, sprint, or something like that. So you look at it very locally, right? You look only at the piece of code which is around some potentially vulnerable place, and you look if it's safe. And checking employs similar approach. So you have some set of properties which are pretty local. You do not need to understand the whole program flow to prove it, and then you try to prove this. An example, pretty well-known work by a team from Stanford University, which was led by Dawson Engler before he created his own company. Anyway, they created a set of tools which were capable of, well, working on the whole source of Linux 25x. And one of the study was verification if kernel uses the user-provided pointers correctly. And this is one of the bugs which the tool found almost automatically. We have a system call named sysquota.ctl, and it takes an argument special, which of course is controlled by a user. And then somewhere in the code, it passes this argument to function lookupbdev. And what this function does, it dereferences this pointer directly here, right? If it's not 0, it dereferences it directly. And of course, if user passes something invalid here, say some pointer into equal to 1 or anything invalid but not null, right? Then we will get a kernel exception when referencing this pointer, which is obviously a bad thing. So to reiterate, the tool was capable of finding such bugs almost automatically. So it's quite an achievement. So this is an example of check-in approach, right? You just focus on proper access to pointer provided by a user, and they check each invocation, each possible place when some incorrect operation can take place. Okay, so from now on we'll focus on this check-in approach, checking only particular properties. And the question is what properties to check. And as you can see from the title of the slide, it's a good idea to focus on integer overflows. There are quite a few reasons. First of all, they are quite proliferated today, right? For instance, in the recent patch for GDI32 DLL, over 50 integer overflow checks were added to a single library. So it's pretty impressive for me. So there was potentially 50 integer overflows in this library. So it's something very unique. They can lead to buffer overflow. Okay, let's have a look at an example in such case, if you're not totally familiar with the subject. Okay, I hope it's visible. Okay, this is an example of the function which has an integer overflow. You can see it takes some argument, which is length, some pointer to data, and it tries to allocate a block of memory, which will be a multiple of 16, right? Nicely aligned. So it checks whether the size is divisible by 16. If not, it adds 15. Then it nullifies the lowest 4 bits. And we should here have a size which is greater than the initial length, but divisible by 16. So there is this assertion, right? That size is greater than the initial length. But of course, it's not true. This is not a correct code, because if len and then size is close to the maximal value of an integer, right, to 4 gigs, if we add 15 to that, it will overlap, right? It will become a small number. And then if we allocate only a small amount of memory and copy the initial length into this small buffer, we'll get a buffer overflow, and probably we can take control over the execution of the program. So this is an example. Okay, the important thing is that integer overflows are well suited to be searched for automatically. The reason being that usually they exist not because of some computation which exists in a loop, right? On the contrary, often a typical buffer overflow happens because you process one element of some array in loop, right? And you write some byte of output also in a loop. But in this case, again, at least when we think about integer overflow in buffer size calculation, usually there is no loop involved. And as I said before, loops are a major problem when proving properties of a program, so that's a good thing that we should not care too much of them. And it's time to introduce our first friend, C-bounded model checker. It's a tool which is capable of, proving some properties of C code. And let's have a look how it behaves in this case. It's a script that invokes CBMC. You simply pass it the name of the file, which function to prove. And if you pass it this vulnerable code to the prover, it immediately reports that the verification failed, and it even presents you a counter example, right? So if size is initially, say, this much, which is the binary representation is here. So if you add anything more, add 15 to that, it will overlap. It will become some small number, and then this assertion will be violated. So that's good. This tool is capable of fully automatically find an integer overflow bug. But it's even better, namely, if you fix this code. How can you fix it? It's simple. just add some check. If size is greater than, well, 10,000, right? You do not expect anything larger to come by, so we exit, right? So this time there is no integer overflow, because if we get to this instruction, we have the certainty that size is small, okay? And now run it again, and this time the verification succeeds. So that's good, because it's apparent that there is a chance that we don't get too much false positives when running these tools. If there are appropriate checks for integer overflow, it should be catched by this prover, and we will not get false alerts, which is a good thing. Look, of course, I could talk a little while about features about this tool. Well, the important thing is, well, it has some features which are not present in other tools. For instance, bitwise operations. Most of the tools, even which are designed to work on C code, do not feature bitwise operations. Another nice thing, it supports pointer arithmetics, function pointers. Well, it automatically, well, uses arithmetics with bounded integers, right? So it takes into consideration the fact that during some arithmetical operations, integer can wrap. But again, it's not very good at handling loops. All it can do about a loop is to unwind it a couple of times, right? So see what happens when you run it once, twice, perhaps 3 times, but that's all. It has some limitations, though. First of all, no source code, so the ability to customize it to your needs is somehow limited. Again, it's not possible to specify loop invariants, so invoke some advanced reasoning about loops. But as I said, we don't want to. We simply do not want to prove every loop one by one, because it takes too much time, too much resources. So that's not a big limitation. The biggest problem that I have come across is that it insists that all pointers must point to something allocated, which is a pain, for instance, if you, well, try to prove properties of a library function, which takes a function which takes some pointer as an argument, right? So at the entry to this library function, you do not know whether this pointer points to anything allocated, whether it's valid or not, and simply CBMC refuses to work on that. So this is a problem. You have to work around that. It's inconvenient. And has some other quirks like inefficient array implementations, and sometimes it requires really unjustifiably large amounts of memory. Like you prove a C code which is like 10 kilobytes, and it suddenly allocates 700 megabytes of memory to prove it. So it's pretty expensive. Okay, so we know that we want to deal with integer overflows. Now, at least initially, you may restrict to some particular operating system. And of course, initially, the choice is Microsoft Windows. I'm not going to insult your intelligence and to explain why it makes sense to find bugs in Microsoft Windows. Anyway, there is quite well-known paper by Dave Eitel titled "Windows has the lowest TCO," something like that, which is TC0, not TCO, of course. So in quite humorous way, he explains why it makes sense for a security researcher to deal with Windows, not with other operating systems. So if you haven't read this paper, it's high time. An issue which is perhaps not well highlighted is that, of course, Microsoft's binaries come without source, right? But the debugging symbols are available from MSDN for free. And it really helps when doing some reverse engineering, or especially when you try to reproduce a vulnerability. Because even if you find something suspicious in a code, and then you try to reproduce that, and if this function is buried very deeply in the function stack, so it may be really difficult to find out what conditions are necessary to trigger this vulnerable function. And if this function is some virtual C++ method, then you may really have a hard time even to find out how it can be called. So it's really difficult. But on the other hand, if you know that this function is named something like process NNTP list response from server, or something like that, so then you can safely assume that, well, this part of code is responsible for handling responses from NNTP server, and suddenly becomes very apparent how to trigger this code. And it happens really that these functions in the Microsoft libraries or binaries have really meaningful names, and it's really helpful. So that's another thing. For instance, if you compare to do I know, HPX or Cisco, the